Hi, welcome back. I want to continue on with this problem here just briefly. And one of the things that you'll notice that we did, we assumed a constant heat capacity here. And so what that resulted in is these isentropic steps. We use these ratios, for example, T2 over T1 is P2 over P1 to the K minus 1 over K. And then we approximated the enthalpy as Cp times T. Now what if you want to account for a variable heat capacity? And it's actually pretty simple to go ahead and modify this equation to do it. So first thing I'm going to do is take account of the enthalpy. So if we want to go ahead and have this be a non-ideal gas, for example, what we can do now is we can go ahead and say that the enthalpy, so H of n, is equal to, and we're just going to use the enthalpy function of air at T is equal to Tn, and that's actually all that we need. This is going to account for a variable heat capacity. So you realize with that one small change, we're now going to have a whole new set of enthalpy values. And the other thing we need to do is we need to change these isentropic relations to set the entropies to be the same. And so first thing we need to do is go ahead and determine what the entropy is. So for example, let's go ahead and say that S1 is going to end up being the entropy of air at T is equal to T1 and P is equal to T1. All right. And then what we can do is we're going to say that S2 is equal to S1 and that S2 is equal to the entropy of air at T is equal to T2, P equals to P2. And what that effectively does is the same thing that that equation did right there. It's going to go ahead and determine my temperature, but with my entropies. And so now I'm going to have a third column, which is going to be my entropy values of 1 and 2. And so we can go ahead and do a similar things here for 3 and 4. And the next one. So I'll go ahead and do that fairly quickly. S3 is equal to the entropy of air, T at T3, P at P3. And then we're saying S4 is equal to S3, and that S4 is the entropy. Alrighty, and so then what we've got is just 2 left. So we go ahead and I'll just pause the video there and finish that out and come right back. Alright, so I went ahead and just did this again for going from 6 to 7 and going from 8 to 9. So notice, just again to recollect, I'm saying that 8 is the entropy at the temperature, then I'm saying 9 is equal to the same as 8, and then I'm able to get the temperature from that equation as well. So now if I go ahead and solve for this, I'm going to go ahead and have again a whole new column of enthalpy and entropy values. It's always a little tough to expand this out when I want it to be, but there we go. There's my entropy values that I need. And nothing else had to change. In fact, what you'll see though is look at my efficiency. My efficiency, that's pretty significantly different than what we had before. The last time we had about 59%, and now we're down at about 52%. So just to recollect what we did, we used the enthalpy function. And it was pretty simple because we had all of our temperatures already, and then these are my isentropic steps, and we use the entropy function. Now for an ideal gas, enthalpy is only a function of temperature, but I'm accounting for a variable heat capacity here. Entropy is always a function of temperature and pressure, and I'm accounting for variable heat capacity by using the entropy and enthalpy functions. Alright, that's it.